purpose during its intended lifetime and be adequately safe. These are the basics. But at the same time, it should be adequately serviceable, meaning that safe है इसका मतलब ऐसा नहीं है कि ponding हो रहा है terrace पे and किसी घर में mixer चल रहा है तो आपके घर में vibrations आ रहे हैं और किसी if there's some fire in one portion of the building does not mean बस कि पूरे building में fire हो जाएगी. So it has to be serviceable. मतलब safety is one thing, but at the same time, the comfort of the occupants is another thing. And our aim in structural design is to satisfy both. After this, our next objective is it has to be economically viable. And our last objective is it has to be aesthetically pleasing. Now, our columns and beams definitely don't make structures aesthetically pleasing. But what happens is we help, we make sure that the architectural intent is satisfied. So we give our sizes, we arrange our elements in such a way that the architectural intent is satisfied, thereby making the structure beautiful. Then we talked about strength, and we talked about a structure being safe and unsafe. So when we say that the structure is safe, it means that there's a acceptable possibility of the collapse, or the possibility of the collapse should be acceptably low. When we say that the structure is safe, it does not mean that the structure can also take a nuclear blast. What it means is under normal conditions, जो भी loads आते हैं, and under very less frequent loads like earthquake and cyclones and extreme winds and accidental loads, the structure should be able to stand. So that is our definition of safety. Then there are other conditions like there should be adequate redundancy that we talked about. Ki matlab, if there is one portion of the structure that is failing for some reason, let us say that there's one particular beam that is really overstressed because of say inadequate design or say increase in the loading without consulting a structural engineer. So if there is failure in one part of the building, there should not be a domino effect. Matlab, if there's a localized failure, there should always be redundancy, meaning that there should be always alternate paths for the host to travel. अगर आप उसको alternate path नहीं दोगे, and that is the only way the load can be transferred, then what happens is, it is going to be a localized failure may result in a global failure of the structure. So ऐसा नहीं होना चाहिए. There should always be an alternate path. एक path में traffic है, तो we can always take another path. ऐसा नहीं है कि that's the only path to travel. वो traffic है, तो then there's no way to move. Then is related to the usability or the comfort of using a structure. So it has to perform satisfactorily under service loads as well, meaning that there should be no excessive deflections, cracking, vibration, and the structure should be sufficiently durable. And fire safety is also a serviceability that is being added. When you enter the industry, you learn that economy is everything. Though we place it at third point, but every decision that a structural engineer takes or an architect takes or an MEP consultant takes has to, the economy has to be kept in mind. All the decisions are primarily driven by economy. You learn this when you actually, start designing structures. So again, basic design considerations: minimum cost, minimum weight. Now, why do we say that the structure has to have minimum weight? Anyone? So क्या हो
To
जाएगा?
reduce the dead load.
So what will happen if you reduce the dead load?
Structure would exert, if there's no live load, then the structure would then be exerting less load on itself.
Okay, which means so what will happen if it exerts a lesser load?
I don't know how to frame that.
Go on, you would frame it in the simplest words possible or whatever you understand.
I don't know.
Okay, no problem. Anybody else wants to add in? What will happen if the dead loads are less?
You need smaller beam and column sizes.
Exactly. If the loads are less, means that your demand is less, meaning that you can provide lesser sizes of beams and columns and ultimately the foundation, which means that you are ultimately saving in a lot of material, which means that you're saving in a lot of cost. Therefore, structure should weigh as minimum as possible. But at the same time, if it's a very tall structure, minimum weight does not always help because it has to have some, uh, you know, self weight to be able to resist or to be able to, deflect within limits when it comes to high intensity winds. So that's a different topic. We're not going to get into that. We're talking about very typical structures. Okay. Then it has to be able to be constructed in minimum time. ऐसा नहीं कि आप structural design दे दोगे, you say it is optimum, but then it is so complicated that the site is taking a long time to do it. So it has to be, it should not be like that. Even there could be some saving in the design, but there could be they could be spending a lot of money in the time that is spent on the site. So it has to be, be able to construct it in minimum time with the help of minimum labor and maximum operational efficiency. Basic design considerations. And while looking at all this, we also started with various design philosophies. We said that there was working stress method, then came the ultimate load method, and finally, today we are, limit states method is used, worldwide, and it is an accepted, I would say, philosophy of design that is practiced almost everywhere. So in limit states method, we talk about safety and serviceability by the use of what are called as partial safety factors. So we have partial safety factors for different limit states. And in terms of understanding the material, we'll look at the design stress strain curves of concrete and steel. So this is just a summary of what we studied in the last semester. So I hope you remember the example of the bike, the brand new bike that we bought, and we said that if you sort of uh, use the bike. Yeah, if you stand beside the bike and then just push it, without actually using it. That's like working stress method, wherein you are limiting the stresses in such a way that the structure is really not tested to its ultimate capacity, and therefore you have a very large margin of safety there. So you end up providing large sizes of columns and beams and so on. Then there was ultimate load method, which in which case you would use the bike say for 5,000 kilometers without any servicing. So ultimate load method talked about making the structure efficient or optimal, the structural design optimal, but did not care about the serviceability of the structure. And then now we are in a position when we talk about both safety and serviceability, and that method is called as limit states method. Now, it's not a question of which method is good and which philosophy is bad. It's about which philosophy is applicable where. For example, if you're talking about designing a water tank, then it is preferable to go with working stress method because the design is extremely critical. You do not want any cracks to develop, and and if you're designing, say another, if you're designing a nuclear reactor, in that case, the kind of safety that we are talking about is extremely important, and therefore, the which method to be adopted depends upon what is the application. But for the very typical structures, majority of the structures or majority of the buildings that you design in your life, limit states method as of now is sufficient. Then what is a limit state? A limit state is nothing but a state of impending failure. So it is a state just before failure, beyond which the structure ceases to perform its intended function, either in terms of safety or serviceability, that it either collapses or becomes unserviceable. So the attainment of any limit state is sort of a signal कि now, if it's a limit state of strength, then the structure is not usable anymore. It has to be evacuated, and it has to be either retrofitted or it has to be demolished. Or if a structure reaches a limit state of serviceability, meaning that now the structure cannot be used comfortably. So you do some repair works, you service it, and then you use it. So that is the difference between a limit state of collapse and a limit state of serviceability. Then we looked at a list of limit states in steel structures. Similarly, we have a list of limit states in concrete structures. So if you look at the list, below the strength column, we have flexure. Then we have shear, torsion, bond, compression. Now, what are these? Now, in the Theory of Structures 5 question paper, there was a question asking us to jot down the various possible modes of failure in flexural members. Now, I don't know, for some reason, perhaps I was not clear enough to tell you that flexure and bending is the same thing. So flexural members are beams because they primarily transfer load by flexure. Therefore, they are called flexural members. Maybe I was not clear, or maybe most of or some of you did not listen to it properly. But you heard the word flexure, and then maybe you remembered कि compression members में कुछ पढ़ा था कि flexural buckling and flexural torsional buckling. So everybody, a majority of you have written the modes of failure of compression members just because you saw the word flexure. So just to clarify, कि flexure is a mechanism by which flexure means bending. It's a load transfer mechanism. So we call beams at flexural members because they transfer load primarily by bending. Okay, so when we're talking about flexural members, we're talking about beams. So the way we have the list that you see on the left, these are basically the force transfer mechanisms. Now, what is a force transfer mechanism? Simple. When you load any element, it has to transfer the load to other elements. So how does it transfer? So it can transfer either the load either by bending, then it is called as a flexural member, or it can also transfer the load by shear, then it could also transfer the load by torsion. Now, a quick example as to when will the load be transferred by torsion. Let us say you're talking about a canopy. You're talking about a cantilever canopy. So the cantilever slab is going to exert torsion on the beam. Now, I'm not going to spend time in sketching it. I just want you to imagine that. Then another limit state of strength is bond. Last time we talked about using steel and concrete together, but they can really act as a monolithic material or a monolithic member only when there's a good bond between them. So bond is an important limit state of strength. And then finally we have compression, which is this particular mechanism can be primarily seen in vertical members like columns and walls. And then about the serviceability, we have deflection, cracking, vibration, fire resistance, and durability. Same standard. I think we've already talked about the philosophy wherein how do we use partial safety factors to make sure that a structure is safe and economic at the same time. So we say that theoretically the capacity should be equal to the demand. What is capacity? All the loads that we are putting and all the bending moments and the shear force and the compressive stresses that are arising from those loads fall under the category of demand. Okay, then capacity is because of the size of your member, the material that you're using in that member. That's capacity. So ideally, your capacity should be equal to demand, and then we have a very optimum structure. But we cannot do it because there are so many variables involved. So there has to be a certain factor of safety. So for safety, the capacity has to be slightly greater than demand. But the question is how much? Like if the capacity is much greater than the demand, it means that your structure is safe and serviceable, but it is not economic. Right? So there has to be some measure as to how much should be the capacity greater than the demand. So our partial safety factors sort of help us solve this problem. Uh, Before jumping into those, we look at a term which is called as characteristic strength. Now, I'm glad that almost all of you have answered this question correctly in the exam as to what is characteristic strength and what is characteristic load. But just to quickly, again revise the example that we saw. So if there are 100 cubes of concrete that you test, so the value of strength below which only 5 cubes, the value of I would say the value of load at below which only 5 cubes fail is our characteristic strength. To define it properly, it is a value of strength below which not more than 5% of the test results are expected to fall. So out of the 100, only 5 will have a compressive strength below this value. The 95 cubes will have a compressive strength higher than this value. So that is called as characteristic strength. And then we have characteristic load. It is a value of load which has 95% probability of not being exceeded during the life of the structure. So if a life, so let us say that we are talking about the college building. So it is intended to be used as a classroom. Let us say a particular room is to be intended to use as a classroom. So the possibility of converting this classroom into a storeroom is say only 5%. So there's a 95% probability that during the life of the structure, the load will not exceed the load of a classroom. Okay, so that value of load is called as characteristic load. So basically, the difference between these two, that is the difference between the load and the difference between the resistance, is the safety margin. If the safety margin is too much, it is safe but not economic. So we sort of reach a golden midpoint by using the theory of probability, by using partial safety factors. So again, quickly revising this. So this is a stress strain curve of mild steel. So the green point that you see is the, let us say that it is the demand that you don't want to exceed. This is the maximum stress. This is the maximum permissible stress in a particular material. And the pink dot that you see is the demand at the working load. So under normal circumstances, under the normal service of the structure, that is the level of stress that we are expecting. So what we do is we sort of use a partial safety factor to reduce the resistance or reduce the capacity. So we move from the green dot to the blue dot by using a partial safety factor for material. And then we move from the pink dot to the, let us say, yellow or orange dot by using a partial safety factor for load. So the basic mantra is we underestimate the capacity and we overestimate the demand. So what we did, so the pink dot was our working demand. So we multiplied it by a partial safety factor to reach the design demand. And this one was our capacity. We divided it by a partial safety factor for material to reach a design capacity or a design resistance. That's how we use partial safety factors. The basic philosophy remains the same, and I've just, whatever I explained, there is just in the form of an algorithm here. So the load we multiplied by partial safety factor to get a design load, and the material strength we divided by partial safety factor to get a design strength. Now, so we had a number of partial safety factors in steel. We had, gamma M0, gamma M1, and so on, so 1.1, 1.25, and so on under different conditions. In the reinforced concrete, we have only two numbers. One is for steel, one is for concrete. So for concrete, the partial safety factor is 1.5, and for steel, the partial safety factor is 1.15. Now, can someone answer as to why is there injustice with concrete that it has a higher partial safety factor?
because it is not a homogeneous material.
Exactly, because steel, is our ideal material. Steel is a homogeneous material. It behaves in a way that we can sort of so if there's a certain behavior that steel is showing in the lab, it is going to see almost the exact same behavior in actual structure because it's a homogeneous material. Concrete, on the other hand, is a heterogeneous material. There are so many different materials involved. So there is coarse aggregate from a source that you might know. There's a fine aggregate from some other source. Then there's water. Then there's cement. Then there's reinforcement, and all of this we are expecting them to behave in a way that we want. Now it's highly unlikely, right? Because it's an extremely heterogeneous material, and therefore we want to be extra safe when we are using a heterogeneous material because there are so many factors that are not in our hands, and therefore we want a larger safety when it comes to concrete, and therefore we have a partial safety factor of 1.5 for concrete, and steel, on the other hand, we have a partial safety factor of 1.15. So again, a very similar partial safety factor table for loads that we saw in the last semester. If you're talking about dead and live, normally it's 1.5. But when we are talking about dead plus live plus window earthquake, then it's 1.2 because the possibility of all of them acting together in the highest intensity possible is low, and therefore we use 1.2. For dead plus wind or dead plus earthquake, we use 1.5, and for all the limits of serviceability, we use 1. Okay. I think in the last semester, we had already discussed the reasons where or the cases in which we use the partial safety factor as 0.9 or 0.8. But since these are atypical conditions and these are very special requirements, we're not going to discuss them right now. So limits of limit state of serviceability, all the partial safety factors are 1. Now, can someone answer this question as to why do we have 1 as a partial safety factor in limit state of serviceability and 1.2 or 1.5 in limit state of strength? See, I don't want you to, like, it's good if you remember the numbers, but it's not about remembering the numbers. It's just about understanding what these numbers mean. So when we say that limit state of serviceability, use a partial safety factor of 1, what does that mean? So let us break down the answer, okay? Serviceability, let us pick up any serviceability. Let us talk about deflections, okay? So what it means is, if I'm calculating deflections in a, say, in a particular beam, then I should consider the service loads or the working loads and not the ultimate loads. Okay, you remember this example that we did, the design of steel beams that we did last semester, wherein when we were designing it for flexure, we multiplied the loads by 1.5. Okay, but when we were checking the deflection, we did not multiply it by 1.5. Why is it that? Come on, it's not a very difficult answer.
For serviceability, you don't want, like, we just want to know when it starts happening, because we don't have to like run out of the building or something. But for when it actually has to collapse, we need to know the exact you know the we have to be more precise with the partial safety factor, because people have to like run out of the safe.
Okay, so it's I would say it's partially correct. Simple. See, there's no structural answer to this. Just simple logic. Anybody else wants to attempt an answer? See, it's very simple. So serviceability deals with the use of structure. When the structure is in a working condition, what is happening in the structure? Okay. So I am interested in the deflections or in the vibrations or in the cracking of the structure when it is actually used or under normal use. Therefore, when I am calculating deflections, I will use its working loads or the loads that are expected in the structure under its service condition. I am not going to care about the deflection at the ultimate limit state when the structure is about to collapse, right? Because anyway, it is not going to be occupied then. I'm interested in limit state of serviceability only when the structure is occupied and only when the structure is under a working condition. Because if under the working condition the structure is deflecting, then I have to do some corrective action so that it is comfortable or so that it is serviceable again. When we are talking, when we are in a state when the beam is now crushing, I am really not interested in the amount of deflection that the beam is undergoing, right? So we talk about limit states of serviceability under service conditions or under working conditions, and we talk about limit state of strength at ultimate limit state or at limit state of safety. Okay, any questions here? I hope that you guys been able to catch up, because every slide that we saw was presented last semester. We spent quite some time there, so just in case there's any confusion or there's something that I do not understand, let me know. Okay, I take it to know. So we looked at this famous stress strain curve for steel, and then most of our understanding of the steel as a material came from only this single curve, stress strain. Tell me, when it is strained this much, how much is the stress that is being developed in the material? Similar to that, now since we are studying concrete, it's imperative that we look at the stress strain curve of concrete, and this forms the basis of how the material is going to behave. So, just like last semester, we are going to go from the material level, first understand the behavior of the material, and then go and understand the behavior of the element in which the material is used. Okay. So let us first try to understand how the material behaves. Now, the stress strain curve for concrete is very simple. there's a parabola up to a strain level of 0.002. You see the strain level 0.002, after which there's a straight line up to 0.0035. So the stress strain variation is parabolic up to this strain value, and then it's linear. Okay. Uh, in this curve, do you think that concrete behaves like a ductile material at any point of time? Or basically, do you see the straight line that you see in mild steel, or say in high strength steel? You always see this initial straight line, and after that straight line, there's this parabolic variation. We don't see such a straight line in concrete. What does that? What does this mean? Okay, let me simplify the
It's not
question.
very elastic as a material. Like once it
Exactly.
distorts, it distorts.
Exactly. It's not elastic. Concrete is not an elastic material. It's a brittle material. In steel, we have this very reliable straight line in which the stress is directly proportional to strain. You remove that stress, steel will go back to its original position. So steel is an elastic material, and therefore you see the straight line wherein stress is directly proportional to strain. In concrete, we do not see any such line, meaning that concrete, if the concrete is not an elastic material. This So this parabola and straight line, that this curve that you see, basically it's an idealized curve. I mean, when you actually test a concrete cube, you would not see such an ideal behavior. Perhaps you could just see a parabola going up and then going down. But this is sort of an idealized behavior that we assume to work out certain equations. Okay. So now let us look at some important, some salient parameters here. First is the maximum stress. So the maximum stress at which the cube sort of crushes, the cube fails, is FCK. FCK is nothing but the characteristic compressive strength of concrete. FCK, characteristic compressive strength of concrete. What was the designation for steel? Anybody? अभी ये तो पता होना चाहिए क्या maximum stress कितना था steel में, and how did we designate it? How did we designate yield stress and how did we designate ultimate stress? कम से कम 50 बार लिख दिया होगा while we are solving numericals. So the yield stress is designated by Fy and the ultimate stress is designated by Fu. In concrete, there is nothing like an yield stress and an ultimate stress. It's only ultimate stress. So the characteristic stress is designated by Fck. Okay. Now, there's always this question as to when you are trying to find out the compressive strength of concrete, you're testing a small cube. Okay. But in practice, you are going to use that concrete to cast very large members and then a very large structure, altogether. So will the cube behave in the same way as the structure will behave? Probably no, because concrete is an extremely heterogeneous material. So you cannot really define how it will behave on the basis of testing a small cube. Okay. And therefore, if we get a characteristic compressive stress FCK after testing a cube, we say that it will have a characteristic strength of 0.67 FCK when it is actually used in a structure. Is the fundamental reason clear? So we see that if the strength of the cube is 60 megapascals, then the same cube, if used in a structure, if the same concrete, if used in a structure, will have a characteristic compressive strength of 0.67 FCK or 2 by 3 of FCK. So 2 by 3 of 60 is 40 megapascals. Is the basic reason clear? Am I not audible?
We can hear you, Bhargav.
Okay.
Bhargav, audible. I got to hear Bhargav. That's right.
Sorry.
No, I couldn't hear you, and I wasn't sure if it was my issue or everyone's issue because my earphones are full of just switch audio.
Okay, is the reason clear as to why we are underestimating the strength when we are using the same concrete that we use in a cube in an actual structure?
Could you please repeat it once? And my audio kind of just went out, and I wasn't able to catch it. What you said.
Okay, repeating in one more time. See, concrete, firstly, concrete is a heterogeneous material. Secondly, uh, concrete, the strength of concrete is a function of its age. You know, it is just like human. So concrete sort of gains its strength over time. Okay, though the rate of gain of strength is different, but the strength of concrete is a function of its age. That's the second thing. And the third thing is that when you test a cube, you are exerting a very basic type of stress. So compressive stress only. So you just test compressive stress. That's it. You crush it, you get a value. But in an actual structure, your concrete is going to be subjected to flexural stresses, compressive stresses, then torsal stresses, and so on. So basically, just by testing a cube in compression, you have to sort of find out how it will behave in different mechanisms. So while testing a cube, the sort of stress is uniaxial stress, but in an actual structure, there is nothing like an uniaxial stress. सब डायरेक्शन से स्ट्रेस आएगा, यहाँ से वहां से ऊपर से साइड से सब जगह से स्ट्रेस आएगा. So basically now you need to, if at all you want a more reliable number, you will have to test the cube in along biaxial or triaxial stress. That's a complicated testing procedure. We're not going to get into that. What we're doing is we are conducting a simple test on a concrete cube. If it gives a certain value, let us say 60 megapascal, depending upon the experience and depending upon experimental studies, we see that if the strength of a cube is 60 megapascals, the same concrete in the structure will give a strength of at least 2 by 3 of 60, which is 40 megapascals. Okay, that's the basic reduction when we move on from a cube to a structure. And then we apply our standard partial safety factor. Partial safety factor is 1.5. So we divide 0.67 by 1.5 and it gives a number that is approximately 0.45 FCK. So this is 0.45 FCK is our design compressive strength, meaning that every element in a particular structure, we are going to design it to have a compressive strength of 0.45 FCK. This is the maximum stress that any member in compression in the structure will be designed to take. So is the reason?
So
Yeah, go on.
so the value 0.67 comes from a set of calculations that we need not understand right now, right?
I wouldn't say it comes from calculation. It comes not just from calculations, but from experience as to how concrete behaves in an actual structure and some experimental sample testing. For example, you tested a cube and then you tested an actual column, and then how different were the results of the cube and the column, and then you sort of compared it, and then we came to a number that is acceptable to everyone. So 0.67 is a number which relates to the behavior of a concrete in a cube in an actual structure. Okay, because of the reasons that we talked about, because it is heterogeneous, because the state of stress is not uniaxial in a structure, and because the strength of concrete is a function of its age. Concrete first gains strength in
Okay.
20 days, full strength it gains, and then it again, uska strength बढ़ता है, and then later on maybe there's a reduction in the strength. So because of all these factors, we don't see the basic purpose of code is to make the life of designers easier. Now, if we start to give a number for every factor, then we'll be dealing with a number of factors and a number of variables, and that would really complicate our design. To keep the design simple, because of all these factors, the strength that concrete can achieve in actual building is 2/3 of what it achieves in a cube. Simple understanding. इतना समझ में आ गया, you've covered all the factors. Steel mein, why did we not do this in steel? Anybody? I mean, we did move from a characteristic curve to a design curve. I mean, I'm sure. So we just divided this by a partial safety factor of 1.15. It was 1.1 or 1.25 in structural steel. But we did not do this for steel. Like, अगर lab में इतना दे रहा है तो structure में कितना देगा? Why did we not do it for steel?
Because steel is a homogeneous material, so it's the
The
same.
answer is the same. The steel is a homogeneous material, and the strength of steel is not a function of its age. The strength is going to remain the same irrespective of when you test it. Like unless it is corroded, or that's a different story. But as a material, it is going to have the same strength. So it's a more reliable material. It's a behavior wise, we understand steel better than concrete, and therefore we have to. Another factor could be that when you're casting a cube, it's pretty easy, right? But imagine, a structural element being cast in situ or cast in site. Using everything that is manual, using manual mixing, manual casting, manual vibration, uh, and so on. So there's just so many variables. There is so many uncertainty that you can't take care of, right? Therefore, क्यूब तो इतना सा है 15 सेंटीमीटर बाय 15 सेंटीमीटर का क्यूब है, आपने कास्ट कर दिया, अच्छे से वाइब्रेट कर दिया, सो ऑन. बट व्हेन यू आर यूजिंग लाइक 1000 times more, or maybe 10,000 times more volume of concrete in an actual structure, you can't expect both of them to behave in the same way, and therefore we bring down our FCK to 0.67 FCK. Simple reason. Is that clear? क्लियर है तो हाँ बोल दो, क्लियर है, we'll move on.
Yeah.
Anybody has any questions? Okay, I take it as a no. So now imagine, like, agar there's a cube that you test and you get a value of say 100 megapascals, okay, just for the ease of multiplying. Let us say that you test a cube and you get the value of the compressive stress 100 megapascals. Still, in a structure, you will say that the concrete has a capacity of only 45 megapascals, because it is ultimately you're going to design it for 0.45 FCK, therefore it's 45 megapascals. Now, what does this mean? Anybody? मतलब 100 megapascal है, आप उसको 90 consider कर लो, ठीक है, 10% contingency तो होना चाहिए. What it means is 100 megapascal का we consider only 45 megapascal.
Swab.
Sorry, someone saying? That is the reason why almost all the structures that we have built so far are standing, because there's enough safety factor in the use of concrete that all the mistakes that we do as designers, then all the mistakes that people on site do during the execution, all these mistakes are getting absorbed in this safety margin from 100 to 45 megapascals. And that is the reason why almost all the structures that you have built so far are standing in a good condition. See, one of our professors used to say that all the buildings are standing only because of partial safety factors. Because particularly considering the practices, on small sites and the small and part-time designers and so on, there is a probability of making so many mistakes. But even after all those mistakes, the structure stands because of this partial safety factor. Okay, moving on. Now जैसे concrete को किया है वैसे steel को भी करना पड़ेगा. Okay, so this is a characteristic curve that we have seen. This is Fy 250 megapascals. अगर high strength use कर रहे हो, so this is for mild steel. This is for high strength steel. High strength steel, let us take an example of 500 megapascals. So this is your characteristic curve. So you move from a characteristic curve to a design curve by dividing all these values by 1.15. So 1 upon 1.15 is 0.7. So the design yield stress of reinforcement is 0.87 Fy. Here, the same case, it's 0.87 Fy. Now, one difference that you notice in this curve and the curve before is that in this curve, you are dividing partial safety factor only in the inelastic region. But ये पिछले वाले curve में we divided it all along. Right? Anybody? What could be the reason? Okay. Again, why this lines have to be with concrete? Okay. In steel, what we saw is, irrespective of what is the grade of steel, up to 250 ले लो, 500 ले लो, 1000 ले लो, the curves always overlap, up to a certain extent, and then they behave in their own manner. Basically, what it means is that the modulus of elasticity, this particular number, is same for steel, irrespective of what is the grade of steel. And this does not happen with concrete. अगर आप 40 ले लोगे, if you compare 40 and 20 megapascals, the curves will be totally different. If I just have to draw it quickly, if this is the curve for 20 megapascals, the curve of 40 megapascals would look something like this. So it is a function of strength. There's nothing in common with these, and therefore we have to take care of. Therefore, we apply partial safety factor right from the origin to all the curves. So if this is my design curve, I apply partial safety factor right from the origin, which we do not do in case of reinforcing steel. Okay. So with this, we'll finish our basic introduction to the course. We have tried to understand, in very briefly, we've tried to understand how concrete as a material behaves and how steel as a material behaves. We've looked at in detail in the previous course. The behavior of reinforcing steel and structural steel is not different. So, any questions here? Milind, would you like to add something?
I really want to stress on that idea when you did discuss about, you did mention about how things happen, how structure still survives on sites which are not very of a huge scale, of a minuscule scale. So it is not often that people go and consult in regular practice, you must be knowing. So it is not often that people go and consult structural engineers or something just for their basic, small units that they're designing and they're trying to come up with. And even then, after having those basic knowledge, they usually follow those standards that, okay, this should be the basic depth of the beams, or this could be the size of the columns, and what kind of members that can come into picture. And still people go with it, and the ship sails on. It doesn't make much of a problem, but it is very important to understand that where you can save those materials, even if you're working on the smaller scales. Having the idea of this structures as a knowledge, it helps as an added advantage, that where you can save the expenses for the client as well, because that makes an impact, and it saves a lot of materials and a lot of it creates a rapport for you as well. So it's quite important. But yes, I do agree with that particular point. People do go with it, and still the structure survives. So that's the let's say characteristics of the material as well, which adds on to it. Yeah, that's something really important to understand. Yes.
Okay, perfect. So you just summarize the importance of why we are looking at partial safety factors. Now, I know in long term, if you're not expect to remember all these numbers, but you are at least expected to understand why the importance of these factors and why a particular structure survives. Irrespective of these small, I would say, errors that we do in designing or in execution and so on. Okay, so with this is the end of our introduction to the course. We'll just take a short break. We'll be back in 5 minutes, and then we'll start with lecture. Okay, meanwhile, if someone has any questions, I'm here to answer.
Hi Bhargav, are you there?
Yes.
Yeah, sorry, but could you please explain the last part of the comparison of the steel and the concrete curve once again?
Yes, I will.
Thank you.
Yeah. Let's resume it after break if that's okay.
Yeah, sure.
Okay, let us resume. So the question that was asked during the break is, try to explain as to why we use the partial safety factor for concrete for the entire curve, but we use the partial safety factor for steel only in its inelastic region. Now, if we look at the curves for different grades of steel, if you look at the curve for say if we 250 or mild steel, we'll see a curve like this. Then if we look at the curve for a high strength steel, let us say Fe415, we'll get a curve like this. And then if we look at the stress strain curve of Fe500, we'll get a curve like this. So what we notice from here is that in its initial range or in its elastic portion, all the grades of steel behave in the same manner, irrespective of what their strength is. Okay, so there's a better, or I would say there's better uniformity in which steel behaves in its elastic region. So we need not apply partial safety factor there because it's certain how steel is going to behave. But on the other hand, if you look at the curve of say M20 concrete or M40 concrete or M60 concrete, all these curves are independent. They do not overlap at any point of time. What it means is that the value of E or the value of modulus of elasticity is a function of what is the compressive strength of concrete. And it's going to be different. If you take an M10 curve, you'll get a value like this. If you take an M80 curve, you'll get a value like this. So along the entire curve, there's no similarity with respect to the grade of concrete. And therefore, we sort of apply the partial safety factor throughout the curve and not just, in the, let us say in this portion where the value is, where the strains are greater than 0.0. We apply it everywhere. Does that clear your question?
Yes, thank you.
Okay, any more questions? By the way, Shravan, why are we expecting, or why is it that we have a lesser count today? Because in the last lecture we had around 74 people. Why is it that we have only 53 today? Is there
No
any
reason that I can think of.
Sorry,
No reason that I can think of as of now.
sorry, Shravan, I can't hear you properly. Is there any overlapping event?
We have encounters right now, but we're going for it late because we'll go after toss at like 11:20.
Okay.
And Bhargav, today the meeting is locked, right?
Yes, the meeting is locked. The reason is, there's
people who have like lost connection, they can't like join back or something. I'm
Okay.
not sure. This is just a thought.
Yeah, I understand it. So, the basic intent is, it has been an observation that when we are, trying to revise what we did in the last lecture, when we are, sort of a short Q&A session, and you've been internally marked on the basis of that, many people leave the meeting, and then once the session is over, then they start joining the meeting, and I do not want to encourage such behavior. Because if you're not in the meeting, you know that I'll not ask a question, and I've locked the meeting in order to discourage such kind of a behavior, and basically I locked it after 15-20 minutes after the lecture started, and therefore I felt that was enough time for people to join in, maybe 5-10 minutes here and there, connection problems, I understand. So that's the intent of locking the meeting. But It is a genuine concern that you sort of uh, you lost the connection and you went out of the meeting and you want to join again, just let me know. I'll sort of unlock it and let you guys in. There's no problem there.
So I think what I can do is I'll keep my WhatsApp active in class, and then anytime I get a text, I'll see it on my PC, so I can tell you that something is here, an issue.
Okay, that
If
works.
someone does, yeah.
That works. I may not be able to see the chat or messages independent. So if you've already sent a message and I'm not aware of it, just let me know. So that I can make sure that no one misses the classes because of some genuine reason. Anyway, this was just to let you know the intent of locking the meeting. I've unlocked it now. People can join in, if they're generally out of the meeting for some reason. Okay, so moving on to our next topic, that is lecture. So the way we are going in this course is that
Also, Bhargav, sorry, what time will we be done by? Because accounting has already started, so then we'll join right after class gets over. So by 11:20, the usual time we will be done, right?
there's a lot of disturbance in your voice. I can't hear you.
We'll be done by the usual time of 11:20, right? Because
Yes, we'll be done by 11:20. Yes.
yeah, so just a general notice to the class that we can join after class.
Yes, and we'll sort of keep this. We'll try to log the meeting 10 minutes after it starts, so that there's minimum, traffic in and out, and people who've joined in can focus on the record. So, as a practice from next lecture, we'll sort of log the meeting after 5 or 10 minutes, depending upon how many participants we have. So what I'm saying is, the way we'll go into this course is that we'll try to understand different, let us call them load transfer mechanisms. So we'll try to understand flexure, and then compression, and then if time permits, shear, and so on. And then with these mechanisms, we'll try to understand the element in which this mechanism is predominant. Now, if it is too heavy to digest, simple. How did we study, structural steel? So we looked at beams, we looked at columns, and we looked at tension member, compression members. So even in that, we did it the same way. We went by mechanism. So there's a member in which the transfer is by tension. So let us call it tension member. Let us study that. Then we went to compression members. So there are certain elements in which transfer load by compression. Let us call them compression elements, and then we studied that. We are going to follow the same pattern here as well. So here we take a load transfer mechanism. Let us say flexure, and doing so, we study the elements in which flexure is predominant. Then we'll say jump to compression, and then we'll study the elements in which compression is predominant. It's very simple. Okay, so let's start. In which type of elements can we expect a significant amount of flexure? Simple gravity structure, okay? We are not talking about any complicated load conditions. In which type of members do we expect flexure?
Beams,
And
slabs,
and any other members? Some amount of flexure, or some intensity of bending of flexure in columns and walls, but you are correct. Predominantly, flexure occurs in beams and slabs, meaning that all the loads that we apply on slabs and beams is transferred to their respective supports by flexure or by bending. Okay, so flexure is commonly encountered in beams and slabs which are transversely loaded, meaning that the direction of load is perpendicular to that particular member. So this is a member, this is a loading, it bends, and that is how it transfers the load to its supports. But जैसे tension members में we had only tension, right? Compression members में, simple compression members में we were only compression. But flexure में ऐसा, like in flexural members, normally we'll also see that there is shear. Now you remember when I say draw a bending moment diagram of a simply supported beam, you also draw a shear force diagram of a simply supported beam, which means that shear and flexure are occurring together in that beam. So flexure does not typically, or any mechanism for that, for that matter, it does not occur individually. If a beam says ki, bhai, I am the flexure guy, shear guy is on the right side, torsion guy is on the left side, and bond wala is on the third floor. It does not happen like that. In any member, say in a beam, there's always a combination. There's flexure, there's shear, there's torsion. Sub ek साथ खिचड़ी पका रहे. It's not individual mechanism that is occurring. But for understanding कि समझना चाहिए कि फ्लेक्चर में बीम कैसे बिहेव करता है, shear में कैसे बिहेव करता है, torsion में कैसे बिहेव करता है, then we club our understanding and then finally design a building, design say a beam. Okay, but mechanisms we look at them separately. पहले फ्लेक्चर समझ लेते हैं, फिर torsion, फिर ये, and then let's try to design a beam. That's a normal design practice. So this usually occurs in combination with shear and sometimes with actual compression and tension and torsion as well. Okay, so just a small discussion. So okay, now we are trying to understand how will a beam behave when it is loaded. So before understanding how a reinforced concrete beam behaves when it is loaded, it is important that you understand how does a homogeneous beam behave. Difference है ना, like there's heterogeneous material, there's homogeneous material. Yeah, bend, like both are gonna bend, that's okay. But in order to sort of develop equations for a material that is extremely heterogeneous, it's important that you understand how does a homogeneous material behave. And then we can extrapolate it. Then हम कुछ partial safety factors लगा देंगे ये वो फलाना ढमका, and then we'll say कि ठीक है, if a homogeneous material behaves that way, we expect a heterogeneous material to behave this way. Okay, so there are certain fundamental assumptions on which we have our bending theory. Okay, to give you a small reminder, this is nothing that is new to you. You must have studied this in your previous courses. I'm not sure which theory of structures, 1, 2, 3, 4, whatever, but definitely you must have studied this. But now we are, digging in deeper and trying to understand how we can apply what you've studied as a theory in an actual design element. Okay, so these are the fundamental assumptions. Oh, before that, if there's still no spark as to what are we really learning, have you seen this equation before? Seen this equation before?
Yes, yes.
Right? This is a bending equation. And I think we also use this equation. I mean, I did not explicitly say that we are doing it, but so when we wanted to find out the moment capacity of a beam, we use this equation. So, so F into I upon Y and I upon Y is Z. So M is equal to F into Z, right? Then we found out what is the value of Z required. How did we do it? So Z required is equal to M upon F. Once we had this value, we went to the steel table and found out value of ZP, which is greater than this Z. So basically, we have been using this, but we are just going back to basics because now it's a heterogeneous material. उसके लिए कुछ derive करना पड़ेगा. So this is a good starting point. So this is our bending theory for a perfect homogeneous material. Okay. So let us start. The first assumption I see, if you lose track of a particular assumption, then perhaps you'll not understand it later. So just make sure that you listen to this properly. समझ में नहीं आया पूछो, ठीक है? But listen to this. So the first assumption is that a normal cross section plane before bending remains plane after bending right up to collapse. Now what does that mean? Now let us take a simple example of this material. Say that this is foam. Let us say, okay. What I did is again I'll just use a sketch. So let us say that I have this material and I want to know bending के बाद क्या होता है. So what I did is I just drew a line right at its center, and then I drew lines at some equal spacing. Okay, so each of these lines, if I cut a section here, now each of these lines represent a cross section. So this is a cross section. So what I've done is, let us say that I have drawn a line here. So this is our central line, which represents this plane. And then I've drawn lines along the, along the side. So if I load it, the lines that were straight initially are still straight after bending. Okay, what does that mean? What it means is, okay. So this line, just assume it now, it might not look straight, but just assume it is straight. So this line, which was straight before bending, so this particular line is still straight after bending. So when I say straight, I don't you can't I don't mean that ये theory inclined over. It's not that. Not I'm not talking about straight in that perspective. What I'm saying is, now this line did not distort नहीं हो गया ये. तो ये यहाँ पे जो straight था ना, bend होने के बाद भी ये line straight ही रहा. It did not get distorted like this. Meaning कि ये जो cross section है, which was a plane cross section, it is still a plane cross section. Now if I look from here, ये cross section पहले ऐसा था, अभी ऐसा है, but it is still plane. हाँ, ऐसा नहीं कि this cross section is distorted. Okay, so what do these lines signify? कि ठीक है, straight है, straight है. What does that mean? What it means is, जितना expansion और जितना elongation lowest point पे हुआ है, let us say 2 mm plus 2 mm elongation, उतना ही contraction सबसे ऊपर हुआ. Okay, and then there's this line, ये हमारा central line. If I measure the length of this central line, let us say 100 mm. Then if I measure the length of this line, कितना आएगा इसका length? Anybody? मतलब, I'm not asking you to give an absolute number 99.85. I'm just asking कितना आएगा? 95 आएगा, 100 आएगा, 105 आएगा, क्या है?
100.
100 mm. Flor, could you please answer 100 mm क्यों आएगा?
Because it's a neutral axis, it will remain the same.
Because it is neutral axis. Neutral क्यों बोलते हैं? Irrespective of, how we load it, the intensity of loading, it is neutral. मतलब it does not develop either tensile stresses or compressive stresses. ठीक है? So इसके ऊपर क्या हो रहा है? न्यूट्रल एक्सिस के ऊपर कौन सा टाइप का स्ट्रेस आ रहा है? कंप्रेसिव. नीचे कौन सा आ रहा है? टेंसाइल. टेंशन के वजह से इलोंगेशन हो रहा है, इसीलिए this particular piece is getting elongated. ठीक है? Compression की वजह से contraction होता है. So all the section, all the entire portion of the element above this is getting contracted. Now what we saw is कि ये line तो straight है. मतलब क्या कि जितना elongation नीचे हुआ है, सबसे नीचे, उतना ही contraction सबसे ऊपर हुआ है. Okay, and center पे it is 0. So it's just neutral axis. So now if I take another point, so if I take, let us say this point, okay, इसमें अगर contraction हुआ है 1 mm का, तो इसमें expansion हुआ है 1 mm का. मतलब क्या होता है कि above and below the neutral axis, the amount of elongation or contraction is same at a same distance. So if I try to draw the variation of strain along this. Okay, if I try to draw this variation of strain along this particular section, the strain would look something like this. So at the neutral axis, the strain is 0. At the topmost fiber, which is in compression, the strain is, say, let us say minus epsilon. The same strain we'll see at the bottom. Let us say plus epsilon. Okay, these plus minus are immaterial. Okay, this is just for our understanding. ऐसा नहीं कि tension को positive, compression को negative. Don't get into that. This is just for our understanding. So this strain is equal to this strain. So if I let us say that this is let us say this is 10 mm. Okay. So this is 5 mm above and 5 mm below. Then if I go to say 2.5 mm, अगर मैं यहाँ पे देखता हूँ 2.5 mm above and 2.5 mm below, यहाँ पे I'll observe कि यहाँ पे अगर strain है, let us say minus epsilon 2.5 mm, then this strain will also be equal to plus epsilon 2.5. Okay, so there's a linear variation in strain in the cross section up to failure. मतलब failure tak, this strain will always remain linear. That is what this assumption means. Then to put it in terms of a cross section, what it says is that a normal cross section. So what is a cross section? Every line here represents a cross section. So a normal cross section plane before bending remains plane after bending right up to collapse. Okay, meaning that this cross section is not going to distort. Okay, which means that there's a distribution of normal stress across the cross section is linear. So that is what we just drew. This is a linear variation of strain across the cross section, and the quantum of strain is directly proportional to its distance from the neutral axis. यहाँ पे 0 है तो strain भी 0 है, यहाँ पे maximum है तो strain भी maximum है. So the magnitude of strain is directly proportional to the magnitude of distance from the neutral axis. Let us call it y. Okay, let us just call this y. So epsilon is directly proportional to y. Is that clear? See, if it's not clear, I could explain again. That's the reason why I'm asking. If it's clear, we can go on and look at the other assumptions. Is there anybody who's awake?
I think it's clear.
Sorry?
I think it's clear.
Okay. Anybody else? Is it clear? Do I need to explain this again? Right. Given the lack of time, I take it as a yes and then move ahead. So that's the first assumption. Okay, plane cross sections. अभी इसका meaning क्या है और what does this imply? ये हम देखेंगे आगे, but just assumption समझ लो. Next वाला. Okay, the next assumption defines what is failure in flexure. मतलब अब आप बोलोगे यार failure in flexure उसमें define क्या करना है? Beam गिर गया तो fail हो गया, simple. But yeah, that is an actual collapse. But we as designers do not consider that as a failure. There's something called as a theoretical failure, after which there can be an actual collapse. But we are not waiting for an actual collapse. Why is that? Why is that we don't call an actual collapse as failure? Anybody?
Because even then, there's a huge issue in managing a structure, right? If it's because, wait, no. Can I just get a second to collect my thoughts?
Sorry. देखो सवाल एकदम simple है. As a designer, why will I not define the failure of a beam as a state when it physically collapses.
Because even before that, it becomes unserviceable.
नहीं, serviceability is a different thing. Okay, serviceability को हम थोड़ा सा अभी पीछे रखते हैं. Now we are talking about safety. So what I'm saying is there is a theoretical definition of failure, and then there's an actual collapse. Why is it that we don't call, or why is it these two are different? मतलब when I say fail, उसका मतलब ये होता है कि बीम गिर गया. Now I'm saying कि ऐसा नहीं होता है. आप लॉजिक लगाओ और आंसर करो ऐसा क्यों नहीं होता है.
Because let's say the structure is almost collapsing, and then some other natural disaster or even a live load applies when
Okay.
people are inside it.
Okay.
And so then that will push it over, well, artificially. Like it won't be the building's own load that takes it down.
Okay.
But
See, the answer lies in the definition of limit state itself. क्या definition है? सबने लिखा है यहाँ. जितने पेपर है सबने लिखा है लिमिट स्टेट का डेफिनेशन क्या है. ऑलमोस्ट सबने, मतलब जिन्होंने अटेम्प्ट किया है वो क्वेश्चन सबने लिखा है. So limit state is a state of impending failure. Okay, the failure is about to happen. It's not actually, it does not say that limit state is a state of collapse. Limit state is a state of impending collapse or impending failure, meaning that it is a state just before failure. Why do we say just before failure? Because we need some time to evacuate the structure. So this definition gives us the time between an impending collapse and an actual collapse. So when we say that it's impending collapse, it's gone. Theoretically, it has failed. It's time to evacuate. So that is when it has structurally already failed. वो collapse होगा, then we just need the time to evacuate, and that is the difference between an impending failure and actual failure. So all the limit states we are talking about are states of impending failure, just before the failure. Okay, and therefore we define a theoretical failure point. And this assumption is related to that point. What this assumption says is that the maximum, or I'll just read it, the ultimate state of collapse is said to have reached in flexure when the maximum compressive strain in concrete in the outermost fiber reaches the ultimate crushing strain of 0.0035. Okay. I think I've lost connection.
They're still around.
Can you hear me? I think I lost connection.
Yes, we can.
Okay. So to put it in very simple words, agar the maximum compressive strain in a beam reaches a value of 0.0035, the beam has theoretically failed, or the beam has reached the ultimate state of collapse in flexure. Okay, so the strain in any section of a beam cannot be greater than 0.0035. Itna simple assumption hai. That's it. Okay. Now, at the same time, there's a related assumption, is that at the ultimate limit state, the strain in tension reinforcement shall not be less than epsilon st star. And epsilon st star is defined as 0.002 plus 0.87 Fi by Es. Now, this equation is, sorry, this equation is, let us keep this equation aside for a moment. Let us try to understand what these clauses mean. Just give me a moment. Okay, so what we are saying is that at failure, मतलब failure कब होता है? जब concrete का maximum compressive strain reaches 0.0035, that is failure. But at the same time, what we are saying is, जब failure होता है ना, तब steel में at least इतना strain होना चाहिए, and that value is 0.002 plus 0.87 Fi by Es. Now I know it is unfair for me to expect an answer from you, but still, if you give a little thought, perhaps there'll be an answer. Matlab, why are we doing this? So we are limiting the strain to concrete to 0.0035. And then what we are saying is, जब ऐसा होता है ना, तब स्टील में मिनिमम इतना स्ट्रेन होना चाहिए, मैक्सिमम नहीं, मिनिमम इतना होना ही चाहिए. Why is that? Can someone answer? Would someone like to attempt an answer to this question? Okay, so we'll try to sort of break up the answer and try to understand. Now, steel. What is the greatest problem with concrete? The greatest problem is that it is not ductile. Okay, it is a brittle material. So आपको पूरे बिल्डिंग में ब्रिटल मटेरियल यूज करना है, बट एट द सेम टाइम आपके बिल्डिंग में थोड़ी डक्टिलिटी होनी चाहिए. व्हाई? बिकॉज अर्थक्वेक्स में या लैटरल लोड्स में डक्टिलिटी इज इंपॉर्टेंट, बिकॉज or even in gravity loading, ductility is important because ductility sort of gives you ample warning before actual failure. Brittle होगा तो क्या होगा, थोड़ा सा डिफ्लेक्ट होके फेल हो जाएगा, आपको पता भी नहीं चलेगा. But if it's a ductile, then आपको दिखेगा कि अरे बहुत सारे cracks आ रहे हैं, the beam is deflecting, so अभी it's time to evacuate. So we want reinforced concrete to behave in a ductile manner. Okay, it will behave in a ductile manner if the steel has yielded. So when does the steel yield? Let us say that it yields at a particular value of strain, which is epsilon st star. इसके आगे अगर strain होगा, तो ही without increasing any stress, the steel will go on deflecting, which means that the beam will go on deflecting without actually collapsing. So what we are doing is we are putting a upper bound on the compressive strain, 0.0035. It cannot go beyond this. But whenever this happens, the minimum strain in steel has to be this. If the strain in steel is less than this number, which means that the steel is still elastic. अगर elastic होगा, तो it cannot undergo a lot of deflection. अगर वो plastic state में होगा, तो ही it can undergo deflection at a constant value of stress. तो ही आपका beam deflect होगा without actually collapsing. Okay, so it is just like when let us say that you're buying a phone. So you fixed one limit to it. You say that I am not going to pay 1 penny more than 25,000 rupees. Okay, so that's like setting an upper limit for the compressive strain in concrete. 25,000 rupees is my upper limit. I'm not going to spend 1 penny more than that. But at the same time, I want at least a Snapdragon 778 processor, or let us say a MediaTek Dimensity 1200 processor. तो आपने क्या किया? Why is this important? Because it has to perform the way I want it to. अगर आप Snapdragon 600, 650 रेंज सीरीज का डाल दोगे, तो I am not okay with that performance. तो आपने दो लिमिट सेट कर दिए. एक अपर लिमिट सेट किया किस चीज का? प्राइस का. और एक लोअर लिमिट सेट किया किस चीज का? परफॉर्मेंस का. तो सिमिलरली यहाँ पे क्या किया आपने? एक अपर लिमिट सेटअप कर दिया स्ट्रेन का, जो कंक्रीट में है, इससे ऊपर हमें नहीं चलेगा. At the same time, in terms of performance, in terms of its ductile behavior, आपने एक minimum strain limit set कर दिया स्टील का, कि स्टील में एटलीस्ट इतना स्ट्रेन होना ही चाहिए. इससे कम स्ट्रेन है तो मेरा बीम ब्रिटल रहेगा, क्योंकि स्टील कभी यील्ड होगा ही नहीं. इसीलिए भी सी स्ट्रेट लाइन, लाइक आई हैव perhaps said in at least 20 times by now कि डक्टिलिटी कहाँ से आता है. There are two things to the behavior of steel. This indicates strength. ये वाला axis indicates strength, and ये वाला axis, I don't know, just a minute. And ये वाला axis represents ductility. Ductility कब आएगा? जब आपका steel yield हो रहा है, तब ductility picture में आएगा. अगर yield ही नहीं हो रहा है, कहीं यहीं पे, यहाँ पे है, तो वो कैसे yield होगा? Without any increase in the stress. तो stress increase करना पड़ेगा yield होने से पहले. So if your steel is somewhere here, then without any increase in the load, it can yield, and that is how we want steel to behave. Easily, we are setting an upper limit for concrete, and we are setting a lower limit for steel. Now, how much percent of this have you understood? See, if I don't get feedback, there is no way for me to understand. I can't see your faces. I can't see, I can't read basically anything. I have to rely on what you say. So, how much percent of this have you understood?
I think we kind of understood, but we have to go back to the recording to just see it once.
Okay, so does everybody agree with her? Is it that you've got a basis, but if you go back and
Yeah.
read,
Yeah.
perhaps that will help you
Yeah, I
understand?
think it's just about revision and sort of understanding it.
Okay, no problem. But at least if the reasoning behind the text and the pictures here is clear, I think you can build on it. The reasoning has to be clear. कि हमारा intent is very clear. Concrete में अगर इससे ज़्यादा strain आया तो it will crush, and therefore we don't want the strain to exceed 0.0035. Oh, I think I've already exceeded our time. I'm sorry for that. I just lost track of time. But steel में इतना strain होना ही चाहिए. Only then it will behave. The beam will behave in a ductile manner. The intent is very clear in these assumptions. Now we'll talk about the next other assumptions and the behavior in lecture. In the next lecture, we'll also have a quiz, and which will be based on whatever we have covered up to this point, lecture number 1 and 2. And I will share this presentation so that you get enough time to revise it. So with this, that's it from my side today. If you have any questions, I'm here to answer. If not, please join your encounter meeting.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Milan, for some reason, I'm not able to stop the recording. Can you please do it?
Yeah, I'll just do that. Wait a minute. Also, I wanted to ask you something.
Yeah.
So